Okay, we're in section 7.2. We're going to graph exponential decay functions. It's very similar to what we did when we came to exponential growth functions. It's just the opposite. So as our x value becomes larger and larger, our y value becomes smaller, which was the opposite of what we had, in 7.1. And the reason for that is because in section 7.1, our variable b happened to be, the absolute value was greater than 1. Here, the absolute, our b is in between 0 and 1. So because it's going to be like some type of a fraction or decimal form, that is in between 0 and 1, that is where the exponential decay function. Other than that, nothing else changes from the first section. And we're going to get a graph that looks something kind of like this, where, again, the asymptote here is still the x-axis. The domain and range for this particular function was x is all real numbers, and the range would be y is still needs to be greater than 0. So when we graph these exponential functions, again, we're still going to use the same main points that we had in section 7.1. We're still going to try to find 0 comma a, still trying to find 1 comma a times b, and negative 1 comma a times 1 over b. So when I'm looking at my graph for example A, I have y equals 1/4 to the x power. So basically what I'm saying is I need to find what A is here. A is 1, so I'm looking for 0 comma 1. And then I'm looking for 1 comma whatever A times B is. That would make it 1/4. And then the next one is negative 1 comma, it would be A times 1 over B. 1 over B, it means you have to flip the, it would be 1 times 1 over 1/4. So that would be 1 times 4, so that would make it 4. So when I write this graph and plot these numbers, I'm going to have negative 1 and 4. I would have 0 and 1. And I would have 1 and 1/4. So again, I'd make my graph look something kind of like this. And again, my domain would be all real numbers, and then my range would be y is greater than 0. So again, we've already established the key points. And then look at example B, my 0 comma, where my a is, which is 6. The next one would be 1, and then it would be comma a times b, so that would end up making it 2. And then the next one would be negative 1, so it would be 6 times 1 over 1/3, which that would make it 3, so 6 times 3 would be 18. So if I go plot these ones, I got negative 1, so I would say that's like way up there somewhere. 0, 6, so again, I'm still off the board here, and then I got 1 comma 2, so somewhere right around there. So when I make my graph, it looks something kind of like this. Again, my domain and range, domain would be all real numbers for my x values, and my range is still would be y is greater than 0. For C, I have my a equaling negative 1, and then my b is 3/4. Keep that in mind. So when I make my points, I got 0 comma, my a is negative 1, and then 1 comma 1 time 1 or negative 1 times 3/4, that makes it a negative 3/4. And then I have negative 1 comma, be what, negative 1 times 1 over 3 over 4, so that makes it 4/3 times up a -1, so that gives me a -4/3. So plotting these points, I got 0 and -1. I got 1 and -3/4, so that would be what? Let's say right about there. And I got -1 and 4/3, so that looks something kind of like this. Again, domain is all real numbers. And then my range here would be y is less than 0, because any y value I get here is going to be negative. Just like in section 1, we have exponential decay functions with transitions. The transition motion does not change. We're still going to do the same format, because first we're going to do is we're going to plot the points in how if there was no horizontal or vertical translations, and then once we plot those points, then we will shift our graph to the appropriate x and y coordinates. So first off, again, I want to first just plot the points as if it was y equals 4 times 1/8 to the x power. So there's no horizontal or vertical translation. So if I do that, I'm going to have 0, 4. If I have the 1, that means a times b, which makes it 1/2. And then c, the next one would be -1, comma, 4 times 1 over 1/4, so that would make it 32. And I'm going to have what, plot 0, 4, and I'm going to go 1 and 1/2. My -1 and 32 is way off the charts at this point, so but if I'm going to change the color here, this tells me here that my h equals a -3, and then my k is a -2. So that means that I'm going to move to the left 3 units and then down 2. So I'm going to go 1, 2, 3, 1, 2. So this is my new plotted point here, and I'm going to go 1, 2, 3, 1, 2. And that's the next one. So when I get my graph made, it looks something kind of like this. It doesn't have it, but if I had my domain, it would be all real numbers. And then my range would be dictated by what my k is, and it would have to be y is greater than -2. Okay. Another one. Again, all I want to do first is plot the points as if y would equal -3 times 1/6 to the x power. I'm not concerned with that +1 or that -7 yet. All I want to know is these points here. So I'm going to go find my 0, a, which is -3. Then I got 1, a times b, which gives me a -1/2. And then my -1 over a times 1 over b, which would make that a -18. So plotting these points, I got 0, -3. I got 1, -1/2, and then my -1, it's way over here. So looking at the translation now, I see that my h equals -1 and my k equals a -7. So that's telling me that I'm going to move it to the left 1 and down 7 units. So this is going to go 1, 1, 2, 3, 4, 5, 6, 7. And then I got 1, and then 1, 2, 3, 4, 5, 6, 7. Plot it there. So it looks something kind of like this, which means my domain for this is still all real numbers. My range is y is less than -7. So that's where my range gets put. Last thing, talk about exponential growth models. This is the equation for being able to find increasing in fixed percentages of quantity over time, and it can be modeled as y equals a times the quantity 1 minus r all to the t power. A is your initial amount, r is your rate of increase, and t is for time. So for the example I'm giving you, it says a company has a total debt of $320,000 between, that's in 1980. It says between 1980 and 1987, it was able to reduce its debt 15% each year. Approximately, what is the company's debt in 1987 to the nearest $1,000? So I'm going to say it's y equals, and then I have, this would be, A would be my $320,000, and then it'd be 1 minus 15%, so it'd be 0.15, all of which is to the t power, and t is 7 years. And if you calculate this out, my y then would equal something along the lines of like 102,584 and 67 cents. But they wanted it to the nearest $1,000, so you can round it up to like $103,000. So that is being able to graph and identify exponential decay functions. So this helps. Till next time.